Recall that we were discussing this permutation in the class group theory video, and in fact what we did with this is that we found out the orbits of these symbols and the cycles of the permutation theta arising from those orbits. So let us once more write those things down. The orbit of 1 is this sec, which of course has 1, and then the image 1 theta, which is, you can see it is 2, and then 1 theta square, which is 1 theta theta. 1 theta is 2, so 2 theta is, again we find that it is 1. So the orbit of 1 consists of only 1 and 2. This set is the orbit of 1. And this also tells us that the orbit of 2 is the same set, because you can clearly see that if you start writing the orbit of 2, it will have 2 and then 2 theta. 2 theta is 1, and then 2 theta square, which means 1 theta, which is again 2. So it also gives you the same set. Then the orbit of 3 is the singleton set consisting of 3, because theta does not change 3. So if you start looking at the images of 3 under all the powers of theta, then you have 3, then 3 theta, which is 3 theta square is also 3, so all of them will become 3. So this is your orbit of 3. And the orbit of 4, it has 4, then 4 theta, which is 5, then 4 theta square or 5 theta, which is 6, then 4 theta cube or 5 theta square or 6 theta. These are the same thing, that is 4 again. So this is the orbit, and this also tells us, just like this one, that the orbits of 5 and 6 also are the same set, and these orbits give rise to these cycles. The cycles of theta are this 2 cycle, this 1 cycle coming from this orbit, and this 3 cycle coming from the 3rd orbit. Okay, so we already saw these things. Now, because we are, again, we have mentioned these things once more, so let us just for once go back to where these things are coming from. Recall that in any set having n elements, we defined a binary relation relating any two objects of such a set. If you take A and B from S, then we say that A is related to B with respect to theta. We in fact used a notation like this: if B is equal to the image of A under the function theta to the power I for some integer I. And what is theta? Theta, of course, is some already chosen element from the permutation group A of S. In other words, theta is a permutation of these n symbols, a permutation on S. And because we have n symbols, this permutation group is nothing but your symmetric group of degree n. And we saw that this relation, this binary relation on S, turns out to be an equivalence relation, so it partitions S into mutually disjoint equivalence classes, each one of which is partition means they are mutually disjoint, each one is a non-empty subset of S and their union is S. And those equivalence classes are what we are calling orbits. Okay. And from those orbits we devised some symbols which look like this, and we are calling these symbols cycles of the original permutation theta. Now note that what do these cycles show us? These cycles tell us what theta is doing to these symbols appearing in the first row. When you look at a cycle, you just know that things are going in this order, from the left to the right, in this sense that the image of 1 is 2. Or let me just, because it is stopping here itself, let me say what the situation is with this cycle. The image of 4 is 5 under our original permutation theta. The image of 5 is 6, and then when you reach the end of the cycle, things cycle back. That is why it's called a cycle. The image of 6 is 4. Just like that, the image of 1 is 2, and the image of 2 is again 1, and the image of 3 of course is 3. So these cycles together tell us what the theta is doing to all the symbols, and you can pretty much understand why they are called cycles. If you imagine that this set is say you imagine the Venn diagram for this set S, where in this case our S is not of course the general S, but this S consisting of these 6 symbols. So you have the elements in the set like this. So what theta does is this. From this diagram and these arrows, you can clearly understand what I am trying to say, and you can also see what theta is doing with all the symbols. This diagram tells us exactly what theta is. Theta takes 1 to 2, it takes 2 to 1, it does not change 3. It takes 4 to 5, 5 to 6, and 6 back to 4. And from this diagram you can see why they are called cycles. And because of this reason, I already said this in the previous video, that although cycles look like vectors, for example this one looks like a 3 vector, a vector having 3 components, but a cycle is different from a vector in that you don't have to start from 4, you can start from 5 also, but then you have to write 6 and then 4. This also denotes the same cycle, because this tells us exactly the same information that is given by this diagram, and what we normally would understand when one writes a cycle like that, that the image of 5 is 6, the image of 6 is 4, and then when you reach the end you cycle back to the beginning. The image of 4 is 5, which is precisely what this one is saying. So when you write a cycle, it does not matter which symbol you start the cycle with, the cyclic order has to be maintained. Okay, so in that respect, cycles are not exactly, although they look like vectors, but they are not exactly vectors. They are ordered sets in which that cyclic order has to be maintained, whereas a vector is simply an ordered set. Okay, so fine. But now we are going to say something else. We are going to now attach a different meaning to these symbols, these cycles, and we will see what comes out from that new meaning. So the author says, we digress for a moment. Leaving our particular theta. That means this theta, and now we are going to discuss things in general. Now before I wrap this part up, do you see one more thing? What I was discussing in the previous video. These structures are cycles, but also these are orbits of these heavenly bodies. You can imagine 4, 5 and 6 as 3 locations in the orbit of a heavenly body that is being that is in motion like this, and the body is driven by this permutation theta. So these are this is the orbit of 4, of 5 and of 6. The orbit of 3 is this itself, and the orbit of 1 and 2, both of them belong to this same orbit. Which is, of course, you understand, it's only an analogy. We are not talking about literal orbits of physical objects. Anyway, so now we are going to attach a separate meaning to any cycle. Suppose that by the cycle we mean this particular permutation. We mean the permutation sign which sends I1 into I2. I2 into I3, and so on, IR minus 1, which will appear before this, into IR, and IR back into I1. And there is more. Keeps every other symbol fixed. Let me just first write the thing down and then we will try to understand. And leaves all other elements of S fixed. All other elements of S fixed. Okay, now let us try to understand what Herstein is saying here. Suppose that by this cycle we mean the permutation sign whose effect on these symbols are these, and such that psi leaves everything else fixed. it seems like we are repeating things. Well, at least in this part we are repeating things. You see, this cycle is a cycle of some permutation, right? For example, you imagine this 4, 5, 6 here in place of this general cycle. If nothing is said, we will just simply know that 4, 5, 6 is one cycle of some permutation. In this case, that some permutation is theta. Suppose theta is in the background. We don't know about theta. So then we can't say from which permutation this cycle 4, 5, 6 is coming, or in other words, it's a cycle of which permutation. That we will not be able to say if we don't know about theta, if just simply this much is given to us. Okay. But now what we are saying, that say we attach a permutation psi to this cycle itself. Now nothing else is given to me, only 4, 5, 6 is given. And what I am saying, or what Herstein is saying here, is that he is imagining that this cycle is linked to a permutation psi, which is this 3, 4, 5, 6. What psi does is that in this part of the set of symbols, I mean this is our S, right? We know that this is S. Okay, well, just for the sake of understanding and for the sake of one example, I am just assuming that this is our S. It may not be, other S's are also possible. Let's just first look at this case. Suppose this is my S and a cycle is given, which of course has its symbols coming from S. Now I am attaching a permutation psi to this cycle in this manner. What psi does is that psi behaves exactly like this cycle on these symbols. And what is the behavior of the cycle? The cycle tells us that whatever permutation it must have come from, that permutation maps 4 into 5, 5 into 6, and 6 into 4, because that's how cycles, that's the information cycles give us. So we make the same thing, we make psi do the same thing to this symbol. So the image of 4 under psi is also 5, the image of 5 under psi is 6, and the image of 6 under psi is again 4. And the remaining symbols are unaffected by psi. Say psi is one such permutation. That is, it does not change the remaining symbols. So this is psi. Of course, this cycle and this permutation are entirely different things. A cycle is a cyclically arranged set of symbols like this, whereas a permutation is a bijective function. These are two entirely different things. However, because of the fact that this permutation has been defined from this cycle, somewhat confusingly, what the author is saying is that they are going to call this permutation psi by this cycle itself. That is, they are going to say that this itself is this permutation, which of course is actually not true. We are just simply giving this permutation this name. We have decided to call this permutation by this name, and the name itself is the cycle, simply because the permutation you can clearly see has been determined by the cycle. That's what the author means when he says, suppose that by the cycle we mean the permutation psi, which sends I1 into I2, that is 4 into 5, I2 into I3, 5 into 6, and like that it goes on, IR minus 1 into IR, which actually in this case is 5 into 6, and IR into I1, 6 into 4, and leaves all other elements of S fixed. These elements are left fixed by that permutation psi. Okay, so it's just defining a permutation using this cycle and then calling that defined permutation by the cycle itself. That is the name we are giving to this permutation. Fine. So that means now every cycle is getting a new, you can think of it like that also, because this ultimately becomes a name given to a permutation which is coming from this cycle. So we in fact somewhat even more confusingly we will now say like this, that the cycle itself is the permutation this. Okay, do you see the thing? A cycle by definition is not a permutation, but this is something we are saying now that this arrangement has been made. And what was I saying back then about having different S's, the sets? Of course, S can change. If your S has other elements, say 7, 8, 9, etc., then you can imagine that the psi will accordingly be defined, particularly like this. For this new S, you will have this psi. For this new S, this same cycle will determine another permutation, or will be thought of as another permutation, and that permutation is this. Four, 5, 6, 7, 8, 9. So that 4, 5, 6 region is just like this cycle. 5, 6, 4. Everything else is left unchanged by this permutation of S. So 1, 2, 3, 7, 8, 9. So if our S is this, then on that S the cycle represents this permutation. Okay, and we will, in fact, since we have given this permutation this name, so we will very carefully, understanding everything that has been done, we will in fact even write something like this, that this cycle is this permutation. Now it seems like this will create so many confusions, who knows what, but you will see that this strange way of calling the cycle itself another permutation ultimately makes things fall in place. Now we will see how. Now, because cycles have been called permutations, or more precisely, cycles have been attached to some actual permutations, each cycle. So we can now multiply cycles also, just like how we ordinarily multiply permutations using composition of functions, simply by multiplying the permutations to which the cycles have been attached. Thus, for instance, if S is the set consisting of these symbols, then this particular cycle 1, 3, 4, 2, 6 is the permutation, this particular permutation 1, 2, 3, 4, 5, 6, 7, 8, 9. I should have started a little bit from this side. It's not a problem, but it looks bad. So first we make the permutation do whatever the cycle is doing in that region. So the image of 1 under this permutation should be 3. Image of 3 is 4. Image of 4 is 2. Image of 2 is 6. And image of 6 is, it should be 1. Everything else is left unchanged by the permutation. So for this S, this cycle means this permutation. We know, I'm again repeating, okay, we need to get used to it. What this really means is that we are given S and we are given a cycle whose symbols of course are coming from S. The cycle does not necessarily, in this particular case, the cycle does not have all the symbols of S. Some have been left out, but it has some symbols. From this cycle, we are defining a new permutation, and that permutation is this, which behaves just like the cycle in that region on those symbols, and it is constant elsewhere. And then what we are doing, we are calling this permutation by this name, which that name itself is a cycle. So that's what we mean when we write then the cycle is the permutation. This is comes from that identification, and we can now write this equal to this. Originally when cycles were defined, if you would have written at that stage a cycle is equal to this, that would have been meaningless, but now it has meaning. And now we come to that issue of multiplying two cycles. We multiply two cycles by multiplying the permutations to which they have been attached, the permutations they represent. Let me just at least keep this one. looking at the permutation, we can readily see what its cycles are. So even if I wrap this part off, we will not essentially lose the cycles. I mean, we won't have to work hard to get the cycles. They can be instantly seen from the permutation. Thus, again, if S has 9 elements, then say we want to multiply these two cycles, 1, 2, 3 and 5, 6, 4, 1, 8. That would mean that we are really multiplying these two permutations. Image of 1 is 2, that of 2 is 3, that of 3 is 1. Everything else is left fixed. So according to our identification, this cycle is representing this permutation times. Now this one also represents another permutation. Image of 1 is 8. Image of 8 is, oh, why am I looking at 8 then? Image of 2 is 2, because that will be left fixed. Or let us first of all deal with these things, otherwise you may get confused. 1 goes to 8, 8 goes to 5, 5 goes to 6, 6 goes to 4, 4 goes to 1, and that's just it. Everything else should be left fixed. 7, 9. Now we multiply these two permutations in the usual manner, how two permutations are multiplied. So let's actually carry out the product. One to two. Again, keep in mind that because in this book we are writing functions on the right side and arguments on the left side, we don't write this. The image of x under f is written like this. So for us in this book, the permutations have to be multiplied in the order in which they appear. So we will start from here and then we will look at this. So that is why image of 1 is 2, image of 2 is 2. So 1 goes to 2. 2 to 3, 3 to 3. So 2 to 3. 3 to 1, 1 to 8, so 3 to 8. 4 to 4, 4 to 1. 5 to 5, 5 to 6. 6 to 6, 6 to 4. And 7 is of course unchanged by both of them, so it remains unchanged by the composition. 8 to 8, 8 to 5, so 8 to 5. Finally 9 is also unchanged throughout. So when we are saying that we are multiplying these two things, that means this, and the result of that multiplication is this. Okay, now you may observe one thing here. You will see that this calculation, you may think that this calculation depends on S having 9 elements, but actually the meat of the calculation means the actual places where changes happen. That is the meat of the calculation. This is not a part of the meat of the calculation, because 9 actually does not, it's unchanged, it's unaffected by the composition, because it is unaffected by both the permutations, both these two permutations. Now you may think that the situation will change if S has more or less number of elements. What would happen if S has, say, 100 elements? Will the meat of the calculation, that is the part where things are changing, will it change? Actually it won't change. You can convince yourself why that is so by, say, of course you don't have to, I am not asking you to take I am not asking you to take a set S having 100 elements, but you at least take S which has, say, 10 or 12 elements, and then you repeat the same calculation with that S, where with that S, of course, the meaning of this permutation will slightly change, only in that now more symbols are available, and the corresponding permutation, strictly speaking, is not this one, of course, because this one is a function from a set S having 9 elements onto S. It's a bijective function. If S is different, say S has 10 elements, then this same cycle will represent another permutation where you will have 10 here. Technically these two things are different, but the part of this world where you have these symbols that takes part in the calculation, truly speaking, and which belong to the part where things are actually changing, that part does not change, no matter what S is or how many elements S has. Or you can understand what I am trying to say, the meat of the calculation, that is the place where changes occur, that part is unaffected by how many elements S has. So you will see that in our identification, where we are attaching a permutation to a cycle, we will actually not mention S. The only thing you will have to guess about S from the cycles themselves is that S has these symbols. Okay, for example, say your calculation started with some S, you don't know how many elements S has, but you at least know that that S has these symbols in it as elements. It may or may not have other symbols, and this calculation actually does not depend on how many symbols S has, because the meat does not change. The actual places where things change, where changes occur, that remains the same. So the identification of a cycle with a permutation actually is not that confusing as it appeared at first sight when we first talked about that, or when Herstein first introduced it. At that time it seemed like things will become very complicated with this strange identification, but luckily and somewhat amazingly, things fall into place and behave as if thinking of this cycle as a permutation is in fact a natural thing. Okay, and the more you work out products like this, the more you will get convinced about this thing, about this fact. Okay, now comes the important thing, and this is why I did not lose theta. Let us now return to the ideas of the previous video and ask, previous means our last video. Of course, Herstein won't say previous video, I am saying it. And ask this question, given the permutation, theta, okay, so the author is not using this theta, but rather this theta. This is also a permutation, no? Let us first do what Herstein has done, and then we will repeat that thing with this one also, because this is easier. It has less number of symbols. So that means I have to again write it. Two, 3, 8, 1. Six, 4, 7, 5, 9. And what are we asking? What are the cycles of theta? Which is rather easy to find, and this is what we did in the previous video. Instead of going through the trouble of first finding the orbits and then writing the cycle, we are going to speed things up a little bit, and directly we are now going to write the cycles of this new theta. The cycles of theta are, let me write it here. We start off with 1. 1 goes to 2. 2 goes to 3. 3 goes to 8. 8 goes to 5. Okay. 5 goes to 6. It seems to not be ending. It will end at one stage, but shall we, by the time it ends, shall we cover all the symbols? That is the question. 6 goes to 4. And then, okay, 4 goes back to 1. So this is one cycle in which already we have 1, 2, 3, 4, 5, 6, 8. So 7 has not appeared, and 7 of course forms its own cycle, and 9 forms its own cycle. What are we going to do now? Now we are going to multiply these cycles, because according to our identification, these cycles represent, each one of them represents a permutation, and see what the product ultimately turns out to be. So here we go. We now multiply these cycles. So we will have this product 1, 2, 3, 8, 5, 6, 4. In the, when you write these symbols, it's somewhat manageable, but then you can imagine you have to write a lot. But let's go through it, it's important. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let us first write the permutation that is represented by this first cycle. 1 to 2, 2 to 3, 3 to 8, 8 to 5, 5 to 6, 6 to 4, and 4 to 1. Do you see that the permutation that this cycle represents looks almost like the original theta, except at these places? 6, 4, have I written it properly? Yes. 7, 9. And what about this one? And in fact, it is theta. If you look carefully, it is theta. And what will this one represent? It will represent a similar permutation on 9 symbols. One, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now this symbol, this cycle represents what? It represents the fact that the permutation it is going to represent maps 7 into itself. Everything else is kept fixed, is left fixed. That means it actually ultimately fixes absolutely everything. And you can imagine that the same thing will happen with this one. So anyway, let's write it. Luckily we have one permutation written here, so we don't have to write the first row. This one maps 9 into 9 and everything else is left fixed. Oh, so in this case, in spite of the size of theta, theta is quite large, acting on 9 symbols. Ultimately, the thing turns out to be quite easy. So easy, in fact, that we can now simply just write what the ultimate product is at once. To calculate the product, it's the usual thing. We will start from here and move rightward. 1 goes to 2, 2 goes to 2, 2 goes to 2. So 1 goes to 2, or should I first of all write the first row? Because the other two permutations actually have no effect, or rather the other two permutations are actually identity permutations. They do not change anything at all. So you can just simply see that the final product will be the first one itself. So 2, 3, 8, 1 64759, which is nothing but theta. So with our let's start from the beginning. Let's start thinking of what we have done so far. We first of all defined an equivalence relation on the set S of symbols. We found its equivalence classes, we called them orbits. From them we devised some cyclically ordered sets in which the theta acts in a cyclic manner. It keeps the things, the symbols on which theta is acting, it keeps things locally circling like that. So those are cycles. Now after that, what we did is that we identified the cycles with some further permutations which can be attached in a natural manner with these cycles. And then when we multiply those permutations back, we are getting the original permutation theta back. So at least in this case, theta is the product of its cycles. But that is not just simply a coincidence which is true only in this case. It is in general true. But before we go to the general thing, let's see what the thing is with this one, because we have this one also. Its cycles are what we already saw. 1, 2, 3 and 4, 5, 6. Now they will also represent, each one of these cycles will represent a permutation. In this case, our S has 6 elements. So the first one corresponds to this permutation. 1 to 2, 2 to 1, everything else is kept fixed. Then it's a product, so we have more here. This one, we have already seen one such thing. This one is going to represent the identity permutation on 6 symbols, because it maps 3 into 3 and leaves the others fixed. Times. This one is not, of course, going to represent the identity permutation. Here the change happens with these symbols. 4 goes to 5, 5 goes to 6, 6 goes back to 4, and the 1, 2 and 3 are left unchanged. Okay, now we calculate the product. And you can see that we can pretty much ignore the permutation in the middle, because it's the identity permutation. So we look at this one and this one. One to 2, 2 to 2, so 1 to 2, 2 to 1, 1 to 1, 2 to 1. 3 of course is unchanged by everything, so 3 goes to 3, 4 to 4, 4 to 5, 4 to 5, 5 to 5, 5 to 6, so 5 to 6, 6 to 6, 6 to 4, so 6 to 4. And this is this theta, our old theta. So in this case also, theta is the product of its cycles. Here also the conclusion is same. Now what we are going to say in the next theorem, next lemma, what is it? I forgot. Is it a lemma or theorem? Is that this is in general true, that if you take a permutation and you find its cycles, then you take the product of those cycles, you will get the permutation back. Now, as a proof, the author of course has written some things, but before going to the general proof, let us see the proof here itself with this case. What is happening here? Let's draw a diagram and try to understand. Why are we getting theta back? Our theta is this, no? This is our S, and these arrows and this diagram as a whole represents theta entirely. Now we have the cycles and the corresponding permutations. If we draw similar diagrams for the corresponding permutations, what shall we get? I need more space. This one takes 1 to 2, 2 to 1 and leaves everything else fixed. This one, which is nothing but the identity permutation, which is this one, leaves actually everything fixed. Every element is its own inverse, that is, it's the identity permutation. And this last one leaves 1, 2 and 3 fixed, whereas we have this cycle 4, 5 and 6. So now now before we see the composition of 3 diagrams, because we are composing these 3 cycles, the 3 permutations, 3 cycles of course we are composing, but actually that means composing the 3 permutations. Correspondingly, the diagrams also can be composed. Now before we look at that, do you see that calling these permutation, for example, this cycle is actually now looking quite natural. It's like we are looking at the place or the location where actually something is going on and neglecting the rest of the symbols because there nothing is going on, nothing interesting is happening when we write a cycle. But if you actually decide to write what is in fact happening with the other symbols also, which is nothing, you would write this. So in that sense, these 2 things really are the same thing. Okay, now comes to the question of composing these diagrams. So we want to see say this is your permutation theta 1, this is theta 2, this is theta 3. We want to see what this product theta 1, theta 2, theta 3 does to the symbols. First we look at 1. What is the image of 1 under this theta 1, theta 2, theta 3? We have already calculated that and we have found that to be 2. That is fine. But do you see anything in this diagram? Theta 1 acts only on, I should not probably say acts, it actually acts on the entire S. All these things are actually the set S, but it changes only this region. Theta 2 does not change this region. Theta 3 also does not change this region. So once you find the image of 1 under theta 1, that is, once you find what theta 1 is doing to 1, that's just it, because then whatever theta 1 does to 1, that is, it makes 1 2, that is unchanged further by theta 2 and theta 3, and that is why we are getting 2. The image of 1 is 2. The same thing can be said about 2. 2 theta 1 is 1, and then theta 2 does not do anything to 1, theta 3 also does not do anything to 1. So the image of 2 is 1. So this part where we have 1 and 2, this local region is just like this one, what the original theta does. The original theta does not change 3, and neither theta 1 nor theta 2 nor theta 3 changes this small local region which has only 3. So their product also does not change 3. And now if we come to 4, 5 and 6, that region, in that region theta 1 does not affect that region, theta 2, actually theta 2 does not affect anything, so in particular theta 2 also does not affect that region, but theta 3 does, and the effect of theta 3 on this region is exactly like the effect of theta on this region. Okay, but we haven't said anything new, we have just simply said all these things in a diagram form. But why is this thing happening? Why are theta 1, theta 2 and theta 3 effectively acting on disjoint regions? That is because we have defined theta 1, theta 2 and theta 3 in that way. Do you see why? Because theta 1 is coming from the cycle 1, 2, and we have decided to attach the permutation, this permutation to this 1, 2, which has its effect only in the first region. So naturally it does not do anything in the rest of S. Then we have decided to attach the second permutation to this 3, which affects only the next region 3. So it has its effect only here, albeit this effect actually is nothing, but still it's an effect. And then theta 3 has been defined to be this permutation, which actually has its effect here in this region, in the third region of S. That is why when you apply this product on any symbol from S, actually one of these 3 permutations has any appreciable effect on this one, and that one for 1 is theta 1, not the others. And how are we neatly dividing S up in these 3 regions so that the entire thing, I mean all the things match and fall into place in this nice manner? That is because Remember where the cycles are coming from. The cycles after all have been formed from the orbits, and the orbits are mutually disjoint parts of S where theta is acting cyclically. So what we have essentially done by breaking things up into orbits and then cycles and then again attaching those cycles to these permutations is that we are breaking up theta to see its effect locally, and those local effects are given by theta 1, theta 2 and theta 3. So definitely when you combine those things you will get theta back. That is the idea, and it's just a simple idea. It looks quite complicated, but it is absolutely simple. And this thing is happening, again I am saying, because we have attached not arbitrarily just any permutations to these cycles, but some special permutations which look almost exactly like the cycle, in the sense that the rest of the things they actually do not matter. Okay, so I think I have been able to explain this in a somewhat understandable manner. In fact, the author himself also says something after writing the proof of this next lemma, where we are going to state the general result, that if the remarks in that proof, which we are now going to see, are not clear, then one is urged to go through one example like this. In the course of carrying out this calculation, the proof itself will become clear. So let us now see the proof, and in fact let us first of all state the result. The ultimate fact from all these things is that when we know about the cycles of a permutation, we know what is going on locally. So that is why any permutation is the product of its cycles. Do you see the fact that the cycles have non-common elements plays a critical role in this whole thing? If you had 3, 4 here and again 4, 5, 6, then things will not appear so, things will not be so simple, and then one region will be affected by the other. But that's of course not the case, because we have set up things in such a way that we get a partition of the S, not overlapping regions. Every permutation is the product of its cycles. The proof is simply this: let theta be a permutation then its cycles are of this form. Oh, we will have to start with a symbol, right? S s theta, then s theta square is there. Let's just write s theta square, and then like that at some stage we will reach the end. So this is an L cycle, its length is L of the form. Now by the multiplication of cycles, as we defined, above, and since the cycles of theta are disjoint, the disjointness is very important. The image of S prime in S under theta, which is S prime theta, is the same as the image of S prime under the product psi of the cycles of all the distinct cycles of theta. So what is Herstein saying? He is saying that because the cycles are disjoint, and so by the multiplication of cycles as we have defined, that is first imagining them as permutations, where only those symbols are changed that appear in the cycle, and those symbols that appear in the cycle and that do not appear in the cycle, they do not change. So under that identification, and since the cycles of theta are disjoint, the image of any symbol S prime in S under theta, that is this image, is the same as the image of S prime under the product of the distinct cycles of theta, and that product he is calling its sign. For example, the image of our that theta, which we saw in the previous video also, under that theta is 2, the image of 1. So if you apply the entire permutation, which is in fact our original theta, to 1, you get 2. But the image of 1 under this product, which he is calling psi, is also 2, because you first apply this to 1, you get 2, and then the others have nothing to do with 2. None of them changes 2. So that's why 2 stays 2, and that is why theta and psi have the same effect on every symbol in S. And the same is true for the other symbols also. So theta and psi have the same effect on every element of S. And hence theta is equal to psi, and this is what we wanted to prove. So here the proof ends. A permutation equals the product of its disjoint cycles. So nice, it's not, the cycles are not a dead end. That is, you take a permutation, you form the orbits, you find the orbits out, then you form the cycles, and you just don't stop there. The cycles will give you the permutation back if you multiply them, provided you first attach that meaning to the cycles, that each one of them corresponds to a permutation. And now, after discussing this thing for quite a while, I think now things have become much more natural to you, to us in fact. Lemma 2-10-1 is usually stated in this form. That every permutation can be uniquely expressed as a product of disjoint cycles. The way we went through the proof, which in fact we understood with 1 or 2 examples, it should already be clear by now why we are having uniqueness here. But if you still don't, if you are not getting the uniqueness immediately, I want you to do this thing. You imagine that you have a permutation theta, which can be expressed as a product of disjoint cycles in 2 different ways. You will then get a contradiction. I want you to do that. But ideally, you should have already obtained or convinced yourself of the uniqueness of this representation of theta as a product. Keep in mind that the cycles must be disjoint cycles, and their product has to be theta. Okay, now next comes something else. Okay, so now it is a kind of decomposition. That is, you have theta, you have been able to decompose it into smaller parts by looking at what theta does on S locally. That is, those cycles, cyclic structure of theta's effect has been revealed by this entire thing. Now, can we break things up even more, break things down even more? And in fact we can. Consider the M cycle. Okay, and M cycle, a cycle of length M which looks like this. One can easily see that this M cycle in fact itself can be broken down like this as a product of even smaller cycles, 1, 3, 1, M. Please verify that this product actually becomes this. It's very easy, you just have to see what this product does to each symbol. You will see that it matches with this. But keep in mind, every time we take the product of a cycle, it's in that sense. So you can then ask me, somewhat terrified, do we have to write the permutations that these cycles are representing, all of them? Ideally you have to write, but you really don't have to write them, you just think of them in your mind. Note one thing, that here there is no mention of S, the set S. So at first it may seem somewhat impossible, or you may be somewhat lost about what to do here. What shall you write in place of 1, 2? What permutation will you write? Just keep this in mind. Whatever you write, that thing has its effect only on 1 and 2. That permutation, whatever it is, depending on what your background S is, keeps all the other symbols fixed. So for example, if you want to know what the effect of this, say the product of the first two cycles on 1 is, then you look at this. 1 is taken to 2 by this cycle. What that really means is that whatever permutation this 1, 2 represents, irrespective of what your background S is, whether it has 3 elements or 2 elements themselves or 4 elements, that same thing, that permutation will take 1 to 2. It will not take 1 to anything else. So you can just simply forget about what this permutation, which is represented by 1, 2, does to the other symbols, because it does not do anything to the other symbols. It does not change them. It only changes 1 and 2, and that is why it makes sense to write in place of all such permutations which this cycle will represent depending on S. In place of all such permutations, you can just simply write this part where changes are occurring. Okay, so this cycle, we will just simply say like this: this cycle takes 1 to 2, and then this cycle does not change 2. So the image of 1 under the product of these two cycles is 2. That way, if you see, you will then see that even in the general case, you can clearly see that in the other cycles 2 does not appear. 3, 4, 5 up to M, all the other symbols are appearing, but 2 is not appearing. So 2 is then unchanged. Once 1 is taken to 2 by this first one, then that 2 remains unchanged by the rest. So 1 is taken to 2 by this entire product, so 1 goes to 2. Like that, what will happen to 2? First of all, this first symbol will take 2 to 1, and then that one will be taken to 3 by this next 2 cycle, and then 3 after that does not appear. So the other cycles have no effect on that 3. So image of 1 is 3 under this product. So the image of 2 is 3 under this product, so 2 goes to 3. In that way you can verify and you will see that this product becomes equal to this M cycle. It's like the permutations are like atoms. Breaking them up as a product of each one of them as a product of disjoint cycles is like looking into an atom and finding that the atom has subatomic particles, electron, proton, neutrons and other things. But then this decomposition further takes you inside of a proton, say. You look even closer, even deeper, and you see that there are 3 quarks. Okay, so it's like that. More generally, we have this M cycle equal to this product of 2 cycles. M minus 1 number of 2 cycles. This decomposition, okay. Now the previous decomposition of, you have an atom and you have the subatomic particles. That is unique. And see here, we are saying unique. And I also asked you to convince yourself why this is unique. This one, however, is not unique. This decomposition of a cycle as a product of 2 cycles is not unique. For instance, to see that, you just look at this 3 cycle 1, 2, 3, which of course has this decomposition, this particular one that we have seen here, 1, 2, 1, 3. But that same 3 cycle also can be written as a product of 2 cycles, in fact 2 cycles in this way. And these 2 things are of course different, because here you see this 2 cycle 2, 3 is appearing, which is not present here. Like that, here we don't have 1, 2. So this thing is not unique. But what can we further say about these decompositions? We have broken a permutation down into a product of disjoint cycles, then each cycle can further be broken down into a product of 2 cycles. So ultimately every permutation becomes a product of 2 cycles, and that ultimate decomposition, of course, because of the lack of this uniqueness, that is also not necessarily unique. Now since every permutation is a product of disjoint cycles and and every cycle is a product of two cycles, we have the following lemma. Every permutation is a product of two cycles. Since every cycle itself is a permutation or has been attached to a permutation in that manner, so this observation becomes a special case of this lemma. If in place of this permutation you have a cycle, so that is also a product of two cycles. Now, before I end this video here, we are going to end here. Let me mention something about what is going to come next. We have seen that this decomposition is not unique, and in fact, the number of two cycles appearing in these decompositions, that is also not unique. You can see, you may think that, okay, fine, so if the two cycles themselves are not unique, maybe the number of two cycles appearing is unique, and maybe for this 3 cycle that number is 2, because we see such things. Unfortunately, that is also not true, because you can, for this simple fact, you can write this 3 cycle also like this: 2, 3, 2, 3, because every 2 cycle has order 2. When you think of it as a permutation, 2 goes to 3, 3 again goes back to 2, 3 goes to 2, 2 goes back to 3. So this product does not change anything. So it corresponds to the identity permutation, and that's why this part vanishes. So you can see that we have expressed this same 3 cycle now as a product of 4 2 cycles. However, here we saw that 3 cycles, same 3 cycle, as products of 2 2 cycles in 2 different ways. But something else here is unique or stays the same. That is the parity of this number. This here you see 2 2 cycles, here you see 4 2 cycles. All these numbers are even, and that evenness will not go. No matter what you do, no matter how you want to write this 3 cycle as a product of 2 cycles, the number of 2 cycles that will appear will always be even. When it is even in one representation, it stays even in the other representations, and when it is odd in one representation, that oddness stays. So there is a way of classifying permutations into the parity of this number, either it is even or odd. Those permutations where this number is even, they are called even permutations, and they form a subgroup of your symmetric group of degree n, an, the alternating group of degree n, and this takes up half of the elements of Sn. We will see why. And so its index is 2 in Sn, and that's why it is a normal subgroup. So we will see all these things in the next video. Okay, and tomorrow is Saturday, so tomorrow again we will solve Gallian algebra problems. So there will be 2 videos, one on groups and one on rings. and on Sunday we have our usual real analysis. So with that I wrap things up, I end the video. So if you want to say something about these things, you can write in the comment section below, or you can see the link in the description. That is my mail address. You can mail me also. So that being said, see you tomorrow with Gallian's exercises. Until then, have fun with mathematics. So this is me signing off from a mathematical room, and my name is Lucifer. Have a nice night.